Alright, so here we're going to finally start talking about forces. Forces and basically the effects that forces can have is one of the first things that we'll talk about, and then also the definition of what a force is. And that's basically it for this video. We'll get more into forces and much more specific in future videos. There's going to be at least several videos that we'll be talking about forces. So this is the first one. You see there, this first picture, that's a yummy s'more. I hope you've eaten recently, otherwise you're probably going to get hungry. And you might be wondering, what the heck does a s'more have to do with forces? Well, I just chose this as an example of one of the things that a force can do. A force can cause a change in size. All right, if you look at this, and I don't know if maybe you haven't had a s'more before, but you start by taking a marshmallow, one of these guys, you put it on a stick and you roast it over a fire. That's not really what we're concerned with. But then you take that marshmallow, which is probably still roughly the same size and shape as it was before you roasted it. Then you're going to put it onto some graham cracker with a little chocolate, and the next thing you do is you smush. So you're going to take that and you smush the two sides together there. And that's going to change the shape of that marshmallow, as you can see. Right? So the smushing motion there of squishing the marshmallow between the two graham cracker pieces causes a change of shape. And size, actually. Changes the size of that marshmallow as well. It gets kind of compressed, it gets squashed, so it's smaller, thinner, tighter than it was before. Because, of course, over here, there's a whole bunch of air inside that marshmallow. Here, not so much air anymore. You've pushed out a lot of the air. So, causes a change in size and shape in that case. Another example, and this is one that we'll look at, we'll actually do a lab with a very similar setup to this before too long in class. And basically what you've got is a spring here, and then we add mass to the end of the spring. And what do you notice? The spring extends. You add more mass and the spring extends more. So this is just to illustrate that forces can cause a change in shape, right? So here the spring is compressed, here it's more stretched out. The shape of the spring has changed. All right, and then one last thing we want to talk about with forces is that forces can cause a change in motion. A change in motion, all right? So the force isn't actually happening in this picture, but you can guess what's about to happen. Here's a person, they're lining up their cue ball on a billiard table, and they're about to strike that ball. Right now, both of these balls, actually not this one, you don't strike a colored ball ever in pool. They're about to strike this white one, that's the cue ball. All right, so both of these balls right now are stationary. Obviously, this person is about to hit this ball, and that's going to change its motion. The force of the cue stick hitting the ball will change the motion of that ball. It will start moving. And then this ball is probably going to hit another ball, and that will change the motion of that ball when the force of this ball striking it. Right, and the angle and all that. Anyway, cool. If you ever play billiards, you know what I'm talking about. All right, so the technical definition of a force is as follows. All right, a force is a push or pull on an object. That may not seem very technical, but that's what it is. A force is a push or a pull on any object. Cool. So what are a couple more examples here? Right there, we've got a guy showing off, perhaps, or maybe he's doing this for a competition. In any case, this guy is pulling this truck full of people. So that's a lot of mass that he's pulling there. He's pulling that in this direction. So he's exerting a force, which we usually illustrate by drawing an arrow in the direction of the force, and the size of the arrow is going to be related to how strong the force is. So this is a pull. This guy's pulling that. An example of a push might be this soldier right here who's doing push-ups. right? What is he pushing? He's pushing his own body, actually. So what he's doing is he's pushing up with his arms against the mass, the weight of the rest of his body, actually, including his arms. So he's lifting his own weight using the biceps and other smaller muscles in his body, in his upper shoulders there, in his arms. All right, so this guy is doing a push-up. Push up, this is a push. All right, so a force can be a push or a pull. Now, you might be wondering, as everything in physics has a unit, the unit of force is called a Newton or newtons, all right? Abbreviated with a capital N. All right, so force, the units of force are newtons. If you care about this sort of a thing, the component units, in terms of standard units, would be, it's a very strange conglomeration. That's why we use a shorter phrase called newtons. But it's kilograms times meters divided by seconds squared. Yeah. So that's why we use newtons. Newtons is, a capital N is much easier to deal with than this whole thing every time we want to talk about force. Okay, and then last thing I want to mention in this video, is this. Basically, we've talked about vectors and resultant vectors. We know that force is a vector, so the resultant of two forces acting in a straight line would be the sum of those forces, so you add them up. One example would be these guys, as they're pushing this cart. It's full of mail, U.S. mail, for one of the U.S. military service, probably the Navy, as these are airplanes and that's the deck of a ship. So these guys are both pushing this cart together, must be pretty heavy, all right? And you can figure out how much force this guy is applying and how much force that guy is applying. I just drew them as being equal. So you would add those two forces together, add them up, and the resultant force might look something like this down here. All right, twice as big, since both of those are equal. And you add them. Now here, I've got a picture of a rodeo event that happens in the US and other places perhaps in the world. And this is called calf roping. So what happens is the cowboy, or the competitor, starts off on his horse. He rides out from the gate when the calf is released and uses a rope called a lasso to catch the calf's neck there, and that tightens down to hold the calf in place. Don't worry, no animals are harmed in this process. All right, so the calf is then roped. The cowboy jumps off the horse, runs over here, and flips the calf over and ties up its legs, and that's it. And then they let the calf go, and everything's fine. All right. So in this picture, the horse, you can see the rope is attached to the neck of the horse. The horse is pulling back this way. As the calf tries to escape, it's pulling this way on the rope, and essentially they're probably roughly equal forces. All right, the horse is trained to pull just hard enough to keep the tension in the rope, and then the calf is obviously not trained for this, but it's trying to get away. So it's pulling this way. So that keeps the tension on the rope. All right, anyway, equal forces, opposite directions. The net result would be no net force. There would be no resultant force in this case. The two cancel each other out. When two things cancel each other out, you end up with zero. So this would be a case of no net force. All right, so there's your introduction to forces as push or pull and the changes that they can cause an object.